A converging meniscus lens. Oh, they have figure. Oh, never mind. We don't have figure, but I think we can solve problem. A converging meniscus lens with a refractive index of 1.52 has spherical surface whose radii are 7 cm and 4 cm respectively. Okay, so they tell us that we'll have a converging meniscus lens. So means by let's break it down. Okay, so if it says converging, then we know that you should have a center which is thicker than the edge. Okay, so that's what they tell you when they say converging. Then they tell you that it's a meniscus lens. So meniscus lens tells you that one side will be convex, one side will be concave. Then they tell you the refractive index is 1.52. That will be our end of our lens material. Okay, so they tell you the spherical surface, both of them will be 7 cm and 4 cm. So 7 cm and 4 cm here will be R1 and R2. You don't know which one is R1, you don't know which one is R2, and it's important to find out 7 cm belongs to R1 or R2. So now we are going to investigate what should we put for R1, what should we put for R2. And besides investigating, we also need to know what are the signs that we need to put to determine the focal length. Okay, so let's give it a try. Converging meniscus lens. How do you create a converging meniscus lens? You can create it by using a sphere of 4 cm, this green sphere here, and a sphere of 7 cm as its radius, the big sphere over here. Okay, and if you overlap it in a way that the larger sphere is in front, the smaller sphere is slightly behind, then you can see that this blue portion here will essentially be a meniscus lens. Okay, so let's snip it out, the meniscus lens that we have, and we can see from this meniscus lens that the edge here will be thicker compared to the center. So in this case, this is a diverging meniscus lens because it has a center portion which is thinner than the edge itself. So we don't want this meniscus lens, we want the opposite of it, we want a converging meniscus lens. So what should we do? We should change the order of the circles. So now we bring the circle which has a radii of 4 cm in front and put this large sphere over here slightly behind. And if we invert the order, bring the blue circle to the front, then we see that this green color portion here is essentially just another meniscus lens. If you snip it out, you will see that the center portion over here is thicker compared to the edge over here. So this is what we are looking for. Because we are looking for a converging, then we say that center must be thicker than the edge. So this second diagram here is a much better representation of the meniscus lens that we want to find. So yep, that's what we get. So let's draw this diagram here. So we know that this green circle here is the smaller circle. Therefore here should be R1, and this R1 here should be equals to 4 cm because this green circle is a small circle from just now, right? So it should be 0.040 meter. Whereas for R2 over here, it's made of a larger circle. So a larger circle should have a larger radius. So R2 should be equals to 0.070 meter. Okay, but it's not that simple. Okay, we still have to determine whether the sign is correct or not. Okay, so let's try and determine the sign. So you have light for this first surface over here, your refracted ray will be inside the lens. You incident here, then you get refracted over here. So the refracted ray is on the right hand side of the first surface. How about the center of curvature? It's also on the right hand side of the surface. Therefore, since they are on the same side of the surface, both on the right hand side of the first surface, you get a positive value for R1. Okay, positive. How about R2? R2, you have your refracted ray coming out from here. Okay, your refracted ray will come out from here. So you know that refracted ray is on the right hand side of the second surface over here. How about the center of curvature? The center of curvature will also be on the right hand side, because if you trace our circle, the circle will be around here. So center is on the right hand side of the second surface. The refracted ray is also on the right hand side of the second surface. Therefore, they are on the same side. Therefore, we know that R2 here should also be positive. So R2 here is also a positive value. Okay, so now we know R1 and R2, and let's look at what the question asks for. The question asks, what is the position of the image if an object is placed 24 cm to the left of the lens? So let's put it down, our object. Okay, our object is 24 cm to the left of the lens. Let's say here is where our object be. Then if you measure the distance to the center of a lens, you'll find that this distance here should be 0.240 meter. Okay, so how do we determine the position of the image? Well, if you want to determine the position of the image, you have the object distance. What you need is an equation called the thin lens equation. Then you can relate the object distance, which is what you have, 0.240 meter, with the image position, which is the image distance, what we can find. But we need to know first what is the focal length for this meniscus lens over here. Therefore, f is a thing that we don't know, and we need to determine the focal length using the Lensmaker equation, which is 1 over f equals to the refractive index of the material divided by the refractive index of the medium minus 1. Then close the bracket for the first component. Second component will be 1 over R1 minus 1 over R2. Okay, so it's a matter of substitution. You know that the lens material is having a refractive index of 1.52, and they didn't mention what is the surrounding medium. If they didn't mention, you assume it's a vacuum or it's just air, which has a refractive index of 1.00 minus 1. Okay, then you have 1 over R1. R1 is positive 0.040. Then you have your R2, which is also positive 0.070 meter. Okay, so if you do your calculation for everything, you'll find that the focal length will be equals to 0.179 meter. Okay, so 0.179 meter, if you plot it back onto this diagram over here, it will be somewhere around here maybe. Okay, so we have cleared up this part, and let me label the distance. Distance from the center should be equals to 0.179 meter. Okay, now we have done this part. Let's get back to the thin lens equation over here. Okay, we know U, we know F, and now it's just a matter of substitution. 1 over U, we know that is, okay, if you want to determine the sign of U, remember that if the object is on the same side as the incident ray, then it's positive. Opposite side to the incident ray, then it's negative. Okay, so from here we can see the object is still in front of a lens, then the incident ray is also in front of a lens. So if the incident ray and the object is both on the same side of the lens, you know that U here should be a positive value. Okay, so it should be positive 0.240, then plus 1 over V, things you want to calculate, then equals to 1 over F. 1 over F here, the F is 0.179, so this should be a positive value. So let's double check whether positive should be the right answer. Well, it mentioned that it's a converging lens. Converging lens is a positive lens, so you should get positive focal length, which is true over here. Okay, so now if you do our calculation, we will find that V will be equals to 0.712 meter, and it's a positive value. If it's a positive value, what does it tell us is the image should be formed on the same side as the refracted ray. So the refracted ray is coming out of the lens over here, and on the right hand side of the lens. So our image should also form on the same side as the refracted ray. So the image should be formed on the right hand side. Therefore, if you try to plot it over here, then it's quite far away, somewhere over here, probably even further away. So this is where your image will form. Okay, so if you want to really put it in words, then you can say this is 0.712 meter to the right of the lens. Okay. Okay, the next question. What is the magnification? Well, we know V, we know U. Now it's just a matter of substitution. We know that M is equals to negative V divided by U. So the image distance is 0.712, a positive value. The U here should also be a positive value, 0.240. Okay. So if you calculate these two things, you should get an answer of 2.97. And remember, it's a negative value. Okay, so what does it mean over here if it's a negative value? If it's a negative value, it tells you that this is an inverted image. Okay, what else does it tell you? If it's larger than 1, then it's magnified. Okay, so combined with V is equal to 0.712, we know that the image should be formed on the same side as the refracted ray. So the image is formed by the intersection of the actual refracted ray that we have. It's not the extension of the refracted ray backwards. If it's extension, then the image should be formed on the opposite side to the refracted ray. But now it's on the same side. We know that this image here is formed by intersection of the actual refracted ray itself. So it should be a real image. Okay, so since this value here tells you it's a real image, so it should be a real inverted magnified image. So let's say our object is over here, then you see that your image here should be inverted but magnified. Probably it's larger, something like this. Okay, so that's a rough idea of how the object and image will be on the around the lens. Okay, so that's all for this question. We apply many things. We apply the lens equation, we apply the Lensmaker equation, and we apply the magnification. So this actually wraps up everything for the subtopic of lens, except that I didn't draw the lens diagram. That's all. Okay, that's all, and that wraps up chapter 7 on geometrical optics.